expect this bicycle wheel to fall down, but it doesn't. Now it's spinning pretty fast. The fact that it's rotating about the vertical as well keeps the whole thing stable. We're going to model this phenomenon by vectors. But what are they? First, there's the spin. Second, the rotation about the vertical. And third, there's a torque due to its weight trying to pull it down and the wire holding it up. Now, when it's spinning, it's the way those vectors form some kind of balance that's going to get us involved in vector cross products. So let's get down to looking at them, one at a time. First, the spin. That's fundamental. It needs to spin for the whole thing to work. Now, it's spinning towards me. That's a vector to the right. What about the rotation? I'll set myself rotating. That's anti-clockwise seen from your point of view. So that's a vector vertically upwards. Now what about the torque? Look at that. One hand taking the weight and the other pushing it down. When it was hanging on the wire, its own weight held it down. But now, I'm having to add a bit more. Oh, thank you. Well, that was quite tricky to hold. I was holding it up here, and a combination of its own weight and my hand pushing it down gave a net force here. That's a torque like this. So what's the vector for the torque? It's that vector, pointing away from me. And the torque's very important. Given the spin, vector there, given the rotation about the vertical, then the torque's necessary to keep the whole thing steady.
So you've just seen two vectors, a spin vector and a uniform rotation vector, combined together to give a third vector, the torque vector here, at right angles to their plane. And that, in essence, is what the cross product is all about. And it occurs all over the place. Watch this. Don't do this to your colour set, by the way. The damage could cost you money. But where's the vectors in that? Well, one vector is from this magnet here. Watch. You see there's a magnetic force vector pushing that other magnet around. And I can show that in another way. Look at those compass needles there. They're pointing north. Now let me put my magnet here, and they all line up to show me the direction of the magnetic force vector. There it is. But there's a more convenient way of getting a magnetic force vector. It's by using this current coil here. It's more convenient because I can switch it on and off. I'll switch it on now. Watch. There you can see the direction of the magnetic force vector. There it is. I'll put it in. Well, I started off by pushing around the picture in this television tube here. But what was it inside the tube that the magnetic force vector was pushing around? Well, let's see what goes on inside the tube itself. The back end of a TV tube contains an electron gun. The front end, a phosphorescent screen. The electron gun shoots out electrons towards the screen, causing the point of impact to glow. This stream of electrons is an electron current. You can see it's a vector. We'll call it an electron current vector. Well, here's a simplified version of a TV tube. Here's the electron current vector here. And you can see the green spot on the tube where the electrons strike the screen. To apply a magnetic field, I use this current coil here, so that when I've got it in position, and when I switch it on, then we'll have two vectors, two horizontal vectors, the electron current vector and the magnetic force vector, both in a horizontal plane. Now, when I switch on, what do you think the combined effect of those two vectors is going to be? Let's see. I'm going to switch on now. The spot's been pushed up. Let's see that again. Off, on, and up it goes. Now, I can represent that effect by putting in this vertically upwards pointing vector here. Well, that looks pretty familiar to me, and you've seen it before too. Remember, two vectors at right angles, a spin vector and a uniform rotation vector, combining to give the torque vector at right angles to their plane. Two vectors combining to give a third at right angles to their plane. And you've just seen it again here. And this situation is very common in physics. We see quite a lot of it. Two vectors combining to give a third vector at right angles to their plane. But what kind of vector combination is this that we're dealing with?
It's going to be a new sort of combination. Now's the time to try thinking about vectors in the abstract. Let's forget about magnetic vectors and rotating chairs and things. Let's look at two vectors, A and B, combining to give a third vector, C, normal to their plane. Now, what kind of vector operations do we know? We know about addition. We know that A plus B gives a resultant which lies in their plane. So it's not addition. That's not our operation. We know about dot product. Now, it can't be that, because dot product isn't even a vector. In fact, it's not one of the combinations we know anything about. We don't really know very much. We just know about the direction. We haven't a clue about magnitude. So let's go back to one of our experiments and try and find out a bit more.
This apparatus is rather like the one I had before, only it's been specially designed to measure magnitudes. The blue trace shows the path of the electron current. The deflection at the end of the grid is just over 1 unit, and that provides us with a good measure of the combined effect of the electron current vector and the magnetic force vector. On this meter, I can measure the magnitude of the magnetic force vector. It's about 2 units. Now I'm going to increase the magnitude of the magnetic force vector, and we'll see what happens. Notice the deflection is increasing too. When we now have a magnetic field of 4 units, and the deflection is about 2 units. So we've doubled the magnetic field, and the effect has doubled as well. So does that help you, Dan?
Let's see. Alan doubled one of the vectors, and that doubled the answer. So it's got to be some kind of multiplication. Now, we know it's not the dot product. We've already dismissed that. So it's a new kind of multiplication. Therefore, we give it a different symbol. We use a cross. That's why it's called a cross product. Now then, we still haven't quite nailed it. We know that it's multiplication, and we know that it's at right angles to these two. But there's a bit more. And in fact, you've already done a problem before the program which tells you practically all you need to know. Do you remember this one? You're asked to work out the speed of a point on the Earth's surface relative to its axis. It's due to its spin. More specifically, you were asked to work out the speed of London. And how did you do it? The distance of London from the centre of the Earth is r. If this angle's theta, then this distance is r sine theta. Now, you know the angular speed of the Earth is omega, about the vertical axis here. So the answer you got was omega r sine theta. But in fact, you know a bit more than that. You don't just know the speed, you know the velocity, because you know its direction as well. It's this. If the Earth's rotating like this, then that's the direction. Now, in fact, you arrived at that answer by combining two vectors. This vector r is in fact the vector displacement from the centre of the Earth. And this vector, omega, the angular velocity vector of the Earth. So these two are combined in such a way as to give this vector, v. And you can see that omega and r lie in the plane, and the velocity vector is at right angles to it. In other words, this is yet another example of a cross product. In fact, v equals omega cross r. But now we know a bit more about it. We know the magnitude of omega cross r. We know it's the magnitude of omega times the magnitude of r times the sine of the angle between them. So let's take that and use that for our abstracted definition of a cross product. Let's define A cross B as follows. A vector of magnitude, the magnitude of A, times the magnitude of B, times the sine of the angle between the two vectors, and direction perpendicular to the plane of A and B.
Well, the remarkable thing is that that same definition works for a whole range of different physical phenomena, including the two you've seen in this program. Here's the television tube again. Here I've given the vectors symbols. The electron current vector I've called C, the magnetic force vector B, and their combined effect that gave rise to the deflection I'm calling the vector F. So, looking at this, the magnitude of F is the product not just of the magnitudes B and C, but also of sine theta as well. So F depends on sine theta. And I'm going to check that out experimentally. Looking down from above, you can see the electron current vector here and the magnetic force vector here. At the moment, the angle theta between them, the angle in here, is 90 degrees. And the effect of these two vectors is to give a deflection, as you can see, of 2 units. Now, what we're going to do is to use the sine theta rule to predict what will happen to that deflection as we reduce the angle theta from 90 degrees. So, starting with theta 90, we have a deflection of 2. Now let's reduce theta by rotating that coil. So the deflection is falling as theta falls. And now the deflection is 1 unit, half of what it was when we started. And the angle theta is 30 degrees, sine 30 is a half, so that is what we expect. Now we can rotate the coil further towards theta equals 0, and the deflection's falling. And now we have theta 0, and the deflection is 0, exactly what we'd expect using the sine theta rule. Well, I've only looked at 3 values of the angle theta, but I could repeat the experiment, looking at more and more values, and I'd find that the sine theta rule fits them all. So it looks as if Dan's definition is quite satisfactory here.
Well, that's good. We've got a sensible definition for the magnitude of the cross product. It actually works. It's the product of the magnitudes of the vectors times the sine of the angle between them. Now, as a result of that definition, we do get 1 or 2 rather funny properties. For example, suppose you take a vector and form its cross product with itself. A cross A, say. What's that? Well, the sine of the angle would then be 0. So A cross A is 0. Now, that one came from looking at the magnitude. Another rather funny one comes from looking at the direction. And this is how we define it in the unit. We use the clock rule again. If I have two vectors, A and B, and I want the direction of the cross product, I think of starting at A and rotating to go to B, so the clock rule gives me a vector that way, like that. So A cross B is in the direction of C. Now then, suppose I'd wanted to form B cross A. The magnitude would be the same. B's got the same magnitude, A's got the same magnitude, and the angle between them hasn't altered. But what about C? Let's try the clock rule. B cross A, that way, opposite to C, minus C. So what have we found? We found that A cross B is minus B cross A. That means we've got to be very careful about the order in which we write these down to get the sign right. So we'd better check our physical problems. Let's try the globe problem. Here we took V to be omega cross R. Omega that way, rotate that way to get to R, so it should be in this direction. That is the way we've got it. So in fact, we've got the sign right. If we'd written R cross omega, we'd have got it wrong.
Right, so you've got a definition of the cross product. Let's now see how to use it. I've got two vectors here, A and B, expressed in terms of the Cartesian unit vectors I and j, so that A and B are both in the ij plane. Let's work out the cross product. A cross B is equal to twice I plus 3j cross twice I plus 5j. Well, first of all, let's look at this term, twice I cross twice I. That involves I cross I, the product of a vector with itself. And from what you've seen, that must be 0. And similarly, the term 3j cross 5j will be 0 too. So that just leaves two other terms. This one, twice I cross 5j, and it leaves also 3j cross 2i. Well, this term contains I cross j. How do we deal with that? Well, first of all, I and j both have unit magnitude. They're at right angles to one another, so sine theta is 1. So the magnitude I cross j is 1. What about its direction? Well, take a look at this. Here are I and j. By the clock rule, I cross j will be a unit vector up here, and that's k. So we now have twice I cross 5j is 10k. Now this term, that contains j cross I. That's the same as I cross j, only the order is different. So j cross I will be minus k. And here then we have minus 6k, giving us finally 4k. And that's the answer. And it makes sense because k is a vector in the plane at right angles to the ij plane that contained A and B.
From what Alan's just said, these unit vectors are pretty easy to use, and it's not too difficult to remember what their cross products give. This little diagram will help. Going round clockwise, I cross j will give plus k. K cross I plus j. If we went round the other way, say j cross I, we'd get minus k. So that just about sums it up. We started with several physical situations. and we found a common vector model for them. For example, the bicycle wheel we started with. That can be expressed in this form. T, the torque, is I, well that's just a constant, a vector omega, the rotation vector, cross the vector S, the spin vector. Now let's look at that situation again, but from a slightly different viewpoint. You see, Alan's holding a horizontal spin vector, but he won't have to exert any restraining torque since he's not rotating. There's no rotation vector, omega. Or is there?
Well, of course I'm rotating. You're rotating. We're all of us rotating with the Earth about its axis at the rate of 2 pi radians in 24 hours. So there is a torque here, but its magnitude is so small I can't feel it.
Let's have a look at the vectors involved. Here's London, and here is the studio floor. There is the wheel Alan's holding, and you can see the direction of the spin vector. Now, the Earth's rotating. It has a vector vertically upwards, like that. And if we look at the cross product of those vectors, then it'll have to be perpendicular to the plane. It's going to be, that is the plane containing the vectors, it's going to be omega cross S. That's a torque something like this. Now, suppose this was mounted on a very sensitive bearing. There'd be nothing to stop it moving. There'd be no torque. And so it would rotate like this. And in fact, it would try to seek out north. Now that's the principle on which the gyro compass is based. And we've set you a problem to do after the program where we ask you to describe mathematically, using the cross product, that phenomenon. To help you see what you're aiming for, let's go and do it. We'll show you how it works. Here's a simplified version of a gyro compass. It's mounted on a meridian which can rotate about this axis. Now I'll set it spinning. And you'll notice that with the Earth stationary, it stays where it is. Now let's make a really big gesture and let the Earth rotate. You see it's seeking north out, which is what we expected it to do. Now that's the problem we're going to ask you to look at mathematically. We're going to ask you to use the cross product to predict that behaviour.